Now, what if that the curve of this function is located under the x-axis? How do we derive our differential area from this? The technique here, again, is to construct thus a small strip of rectangle in which this is our base and this is our length. From the constructed rectangle, we can formulate a differential area that is equal to y dx, same as before. But y is located under the x-axis in which it has a negative value. So we will need to put a negative sign before y. So applying the integration on both sides, in which our graph is evaluated from A to B, then we can say that this area is equal to the negative integral y dx evaluated from A to B. So this will be our equation 2. Now let's proceed to our next example. We will need to find the area of the curve y is equal to negative 1 over x, and it is bounded from x is equal to 1 to x is equal to 2. Looking from our function that y is equal to negative 1 over x, you will notice that we have a variable in the denominator, in which this is an example of an asymptotic function, meaning that if x is equal to 0, then our function will be undefined. So we will have a graph that will look like this. This is an example of asymptotic function. Looking from our condition that our area is bounded from x is equal to 1 and x is equal to 2. So we will focus in this one. So in order to clarify this assumption, we will need to construct a table of values of our function. Looking from our function, that is y is equal to negative 1 over x. Now, if x is equal to 1, then y is equal to negative 1. Now, if x is equal to 2, then y is equal to negative 1 half. That is negative 0.5. That is 2, negative 0.5. Now, if you will continue to create the table of values, you will notice that as x increases, then y decreases at is approaching to 0. But it will never be equal to 0 since this is an asymptotic function. So from the table of values, this will help us to plot our function, to plot our graph. That is, now we have our first point, that is 1 and negative 1, then 2 to negative 0.5. Tracing these points, we will have, and it is bounded, x is equal to 1 and x is equal to 2. By constructing our small strip of rectangle, we will have a negative y here and dx. Then we will have a differential area, that is dA is equal to negative y dx. And if we evaluate the integral of our differential area, we will have a is equal to the integral negative. We will take out the negative since this is a constant value of y dx evaluated from 1 to 2. Now, the next step here is to equate our y here in terms of x. From our problem, this y is equivalent to negative 1 over x, in which the negative sign multiplied by the negative sign the outside of the integral will become positive. Then the area is equal to the integral of 1 over x dx evaluated from 1 to 2. This integral can be evaluated in which this is equal to the natural logarithmic of x evaluated from 1 to 2. So this will become ln2 minus ln1, in which this is ln2 over 1, in which our area is approximately equal to 0.6931 square units.